Hello, in this video I wanted to say a couple things about the seminal paper on verifiable random functions. So this won't go through the whole paper, I just wanted to discuss a few points which I found interesting. So diving right in, let's skip down to the main result. Apparently the very first construction of VRFs are based on the hardness of RSA. This is in contrast to future results that are based on bilinear maps over groups, and those actually use a variant of the Diffie-Hellman assumption. So it's interesting to know that VRFs can be constructed from more than one hardness assumption. Next, let's take a look at the properties presented in this paper. So here we have the very first definition of VRF. This is the generator function G, the main function F, and the verification function V. These have pretty much remained the same over time. Next, if we look at the properties, the first one is domain range correctness. All this says is that the input and output parameters match up correctly. In fact, future iterations of this definition have become simplified over time, and they actually no longer talk about domain range correctness. Next is provability. This is actually stated in terms of a probability. So here this says the probability that the verifier on correct inputs is correct with probability 1 minus a exponentially small value. In other words, it's correct with overwhelming probability. So more modern definitions actually remove the probabilistic part of the statement. And actually the same is true of uniqueness. So for uniqueness, this states the probability that the verifier on two different random inputs based on the same commitment X is going to accept with negligibly small probability. And in fact, we can compare this definition to a more recent version. For example, let's look at this paper from a couple years later. If we skip down to the definition, we can see that both uniqueness and provability are absolute statements. They are no longer written in terms of a probability. So in fact, the very first definition has been simplified over time. Next, let's talk about pseudo-randomness. So this is described in terms of a challenge to an algorithm T composed of two parts. Here's how it goes. First, we start with the generator to obtain a key pair. Next, we take the public key. We give it to the first part of the algorithm T along with oracle access to F, so it's allowed to query F on arbitrary inputs. And we ask that it outputs a value X, which we can think of as a challenge. We can skip state for now. Next, once we have X, we flip a coin and we do one of two things. In the first case, we evaluate the function F on the input challenge X to obtain V. Or in the second case, we just choose V completely at random. Next, we take the second part of the algorithm T. We feed it the value V and the value state. So actually, we can think of state as the first algorithm passing supplementary information to the next. Once again, this T is given oracle access to F, and we ask that it outputs a guess. The idea is that it's trying to guess the output of R. In other words, it's trying to tell whether or not we constructed V based on the function F, or if we just constructed it completely at random. And what we want is that T should succeed with no more than 1/2 plus a slight advantage. In other words, it can always randomly guess and in that case, it will succeed with probability 1/2. But if it's not able to do much better than that, then essentially T cannot distinguish the case between a completely random value versus one generated from F. And in that case, we can claim that F is pseudo-random. Moving on, let's talk about how the main statement was proved. So actually, first, the authors construct a similar object called a verifiable unpredictable function. And the reason they do this is because this is used as an intermediate step in their proof. So what happens is they start with the hardness assumption. And from here, they construct a verifiable unpredictable function. And then using a VUF, they construct a verifiable random function. So they essentially prove this in 2 steps. So what exactly is a VUF? It is exactly the same thing as a VRF, except instead of the pseudo-randomness property, they replace it with a unpredictability property. So this is also stated in terms of a challenge. The difference is T is asked to output a pair of values x and guess, where we want guess to be the output of the function f. And if T is not able to output a pair like this, we essentially say that the function f is unpredictable. Okay, so moving on to the main statements. So first, proposition 1 states that if we have a VUF, we can construct a VRF. So that is essentially this step here. Proposition 2 essentially takes one VRF and transforms it into another VRF with different input and output lengths. So actually, this statement here has a slight typo. It should actually read B of k equals A of k minus 1. And this is immediate if we look at the details of the proof later on. Next, the authors describe exactly what they mean by hardness of RSA. And then the last statement they prove is that from RSA, we can construct VUFs. So that is this step here. And actually, proposition 2 is used in this part of the proof as well. So if we put all of that together, we get the main result of the paper, namely, assuming RSA is hard, then we can use that to construct verifiable random functions. And that is essentially the paper in a nutshell. The rest of the paper goes into the details of how they prove each of the propositions. And that is all I wanted to say on this paper. Thank you for listening.